start again. Yeah, okay, but I think logarithmically, most of the shock is on the outer scale, or at least it does exist there. Now, this simulation was done for intermediate mass black holes, but if you extrapolate it to supermassive black holes, then you get that the energy dissipated by the shocks is about 10 to the 51 ergs. And this should ring a bell, because this is more or less the upper level of what we see. So, so what happened is that Yair Alkavi was here about a year ago showing the result that he had. And when the talk was, that was, I think, the first time I ever heard about tidal disruption events. And then when the talk was over, Tzvi told me, hey, Gilad, I think you're not doing anything special right now, right? Do you mind doing some calculations? So we went down the stairs to Tzvi's office and desperately looked for an envelope, but there was none. So both of us went home to look for old bills or so, find an envelope. And then next day we met and we both brought our vacant envelopes. And that's pretty much what we had. We had a black body radius of 10 to the 15 centimeters, a black body temperature of 3 times 10 to the 4 Kelvin, a total energy of 10 to the 51 ergs, and a line velocity of 10,000 kilometers per second. And this is indeed what we usually see in most candidates. In fact, there is even a bonus, because if what gives this signal is the outer shocks, then we naturally get a T to the minus 5/3, because nully shocked metal simply follows the mass fallback rate. And this is pretty difficult to explain in any other of the propositions, because, for example, if you take Eddington threshold, then we expect between a year and 3 years of constant luminosity due to the luminosity being cut at the Eddington level. Or if you take a mechanism with reprocessing, then there are so many proportions to keep in the way between the mass fallback rate and all the stages until you get some signal out of the reprocessing. And in the way, you have to ignore many, or to tune very well many factors. So it's not really clear how you get a T to the minus 5/3 out of all this processing. But there's of course a few caveats in this model. One is maybe the 10 to the 51 or 10 to the 50 is just a selection bias. So we know in the case of Yair that he was actually looking only for about 10 to the 50 between the ordinary 10 to the 49 erg of ordinary supernovae and the 10 to the 51 and 10 to the 52 of superluminous supernovae. So I don't know well enough about other searches, but it could be the case that we're simply only looking at the 10 to the 50, 55 ergs. And that's why we don't see 10 to the 53, for example. The same story could be with the T to the minus 5/3, because for two reasons, actually. One is that this has been the hallmark for TD searches for many years. And another one is that you can sort of manipulate this, power. You can change the T0, the time of the first orbit. If you're not exactly at the T to the minus 5/3, but say T to the minus 6/3, well, you can play a little bit with the first orbit and then get T to the minus 5/3. So maybe this is also a selection bias. But let's just imagine that we're 10 years ahead, and we've gathered a huge sample of TDs. And let's also imagine that now we have TDs ranging from 10 to the 49 ergs to 10 to the 53 ergs, filling all this gap. And we also have all kind of trends of light curves. So say from a luminosity, from a constant luminosity all the way to, I don't know, T to the minus 4. Would it even be interesting to try to find a common explanation to all of this? I don't know. I'm just raising the question. I know that an important motivation for our paper was the snapshot that we had at that time. We saw some similarities, and that gave us the idea. If we instead had a huge spread, I don't know if we would have any motivation to try to find a common explanation to all of this. So I think it's kind of an open question, and interesting to see what will come by. Another caveat is that while we were doing these calculations, we're assuming rather a circular flow, looking at the simulation. But then for supermassive black holes, the flow is probably more elongated, and at least in some of our calculations, we have to better adapt it to a more elongated flow. But probably the most interesting question is, where are 10 to the 53 ergs hiding? If what we see is the shocks, and we think it is the shocks, then what happened to all the rest of the energy? So maybe this is a good time to compensate for the ungiven credit in this slide, which is only partial. There aren't all the proposition here, but we're gonna I'm gonna do the following deal. So because I didn't give you credit, I'm going to give you more credit than I gave you before. So I think that your mechanisms are in fact so efficient that rather than bringing the energy from 10 to the 53 ergs to 10 to the 51, they'll probably bring it all the way down to 10 to the 50. And what's left is the shocks. So I'm giving you even more credit. But there's, of course, the chance that you like the way you tailored your theories, and you like them to bring it back, to bring you down to 1% and not 0.1%. So for that chance, we also have our own explanation, and Zvi was presenting it. That's the elliptical accretion. If elliptical accretion happens, then we don't even get to any of these scenarios, at least at the beginning. Now, I don't know to tell you how much elliptical accretion can carry on its own. If we would make a bet, I would probably agree that it should do at least half of the logarithmic distance between 10 to the 53 erg and somewhat less than 10 to the 51. And the remaining should probably be either any of these or some combination of these that would do the other half of the distance to what we actually see, to what we actually see from accretion, if what we're seeing is the outer shocks. So I think I didn't even use my 2 spare minutes, right? Well, I don't need them.
So, I mean, one of the points you didn't put on the ways that you can reduce it from 10 to the 53 to 10 to the 51 is reducing the star's mass and partial disruption.
Right.
And the IMF is biased towards low star masses. Even for top-heavy IMFs, the slope is just different. But it's still biased towards low mass stars. And partial disruptions are going to be more common than full disruption. The second thing is that if the Eddington limit needs to be respected in the sense that it cannot exceed the Eddington limit through the disk, the shape of the light curve is going to be very different if you're exceeding the Eddington limit. And it's going to look something flat and then having a decay at much later times.
I agree. But we're not seeing any flat part of it.
We do see things like that, but people are unwilling to say that those are HUJI because they don't look like your standard transient. They last maybe a year above the Eddington limit, and then they decline. So, I mean, those might exist where you have things that are supposed to be releasing close to the 10 to the 53 ergs of energy, but the Eddington limit is respected. The third point I just want to make is we do see some evidence now for winds coming from TDE suggesting that the Eddington limit is actually being at least flirted with. So there's 14LI shows evidence for outflows. PS1 11AF showed this magnesium 2 feature that seemed to be leaving at 15,000 kilometers per second. So I mean, I just would make the argument that there are indications of the Eddington limit being respected, and perhaps the energy problem not being as severe as it's being portrayed to be.
Yeah, I agree. I think that it's an open question, and it's interesting to see what we'll gather once we are willing to let go of some of the pre-assumptions. And I think this is happening as we were talking or doing this last year.
You mentioned examples of flares lasting a year. I couldn't quite tell whether you knew that there are such examples or whether they might possibly exist.
I've seen them from pan stars, where there are maybe 3 or 4 examples of AGN turning on to a flat level, staying on for maybe 2 years, and then having a sort of power law decay afterwards. And they're attributed to AGN activity, but they're not.
Now you spoke about AGN. Are they AGN continuing and they just get brighter for a year, or are they really dark before and after?
That's the proposal is that they've gone up in flux by a factor of 50 from at least prior to when they go through an active state. It's not clear to me if they have signs of AGN activity prior to that, like weak AGN activity. I think it's an open question actually. 14LI, for instance, is a radio source prior to having the disruption that we're all claiming, suggesting that it actually was a low luminosity AGN prior to turning on as a tidal disruption. Chelsea McLeod is the one who's done some work on this in CanStar. Some of these flares that turn on for a while and then flatten off and then decay. I guess what I'm just trying to say is that we are picking, maybe not on the power law aspect of the transient, but we're picking on the flare aspect of the transient, the fact that it peaks and over a relatively short time scale then decays. And I think when you see the Eddington, in principle, if the disk is limiting you, you'll just go up to Eddington. Maybe you can have a logarithmic increase above that level, and then you'll decline. And so we're observationally biased against selecting those particular times.
No, but sorry that I have to cut you, because we have some other questions. My remark on that is that let's focus on the events that we see. And the event that we see, we don't see the Eddington limit. So
we do see the Eddington limit. We have winds, right?
the winds are not at 10 to the 53 hertz.
They're not at 10 to
The winds are 10 to the 49, 10 to the 40, 10 to the 50. They are not at 10 to the 50 hertz. So there is a limit to the level that one can twist the data to fit the model.
On the topic of Assassin 14LI, how does the circularization paradigm deal with the X-ray luminosity from this key? In your view, is Assassin 14LI an unusual key in which circularization was strangely efficient, or is this something that naturally occurs and is just blocked by viewing angle? If it's the latter, it seems like reprocessing to some extent is inevitable.
Yeah. So I should have said that this is mainly based on on the optical to UV events, which are the majority. Obviously, the X-rays are where we do see X-rays, especially if we see a lot of energy, is either a different mechanism or a special viewing angle or so. So this is based on thinking about the majority of the events and not probably two events where we do see X-rays by now.
Just brief comment, because it seems to me that if there's a fraction of events in which the paracenter in gravitational units is large enough that the shocks occur at large distance, and we can argue about the distribution of that quantity, and I think it's not at all clear, where the peak is, but to the extent that it seems likely that there are some of them, then there will be these shocks at large distance. And generically, that's also one of the few regions in the whole system where the cooling time is not incredibly long. So if there's heating, and the cooling time is basically of order the mass return time, then there ought to be light. And the light you'd expect looks like this.
And I concede that you should expect light from the circularization shock directly. I think that is an important point to make. It should be a contributor to the total light. I just disagree that you can completely get rid of the disk component of the problem. That's basically my main quarrel with the present solution.
So let's assume that the outer disk gives 98% of the observed emission, and that there are some additional components which contribute to the visual, and some other components which contribute to the X-ray. So if we agree on that, I think we are satisfied.
Well, it's not clear.
I suggest that the organizer should give another 2 minutes to everyone that agrees with the suggestion.
Okay, I think that we are running out of time, so one more question.
Yeah.
So I mean, in this scenario, what you might imagine would be that you get this optical low temperature flare coming out at some stage, visualization. And then at some stage a little bit later, months later possibly, then you're going to get the disk coming in and actually accreting, and then you're going to get another flare, which is going to be in the UV and the X-ray form. And I don't think we've ever seen that UV flare with an optical precursor, or vice versa.
So
I don't see any reason particularly why these two things should be simultaneous in this case, which you do see quite. I mean, even the PS110J8, the UV and the optical flares are the same thing.
So yes, Yair yesterday said that he was starting to look for a second signal from the accretion. My opinion is that you might not see anything, because if the accretion is according to the now so-called Jerusalem bagel, then you're not supposed to see that, or you're supposed to be to see a very faint signal, and if you're not sensitive enough, you'll just miss it. That's a possibility. It still needs simulations to be better checked.
So one last question while Nathan is setting this computer.
Another observed property is it's pretty smooth light curves without any RMS variability. You're only at like the 1% level, which is even less than what some AGN disks do. Whereas these shocks in the simulation, they're coming in, and so it's a stochastic process. So do you have an explanation for smoothing the light curve?
What do you mean by smoothing the light curve?
Well, I mean, you have
it's specifically the light curve you expect
spikes,
is
right, and so you should get a spiky light curve if the optical photons are coming from dissipating the energy in the shocks. But in fact, we see this extremely smooth light curve. So so it's just this one photron, nothing else.
I agree. It's a good question. It probably depends on should depend on the geometry of the flow that you produce, and what you're saying that we're getting a too symmetrical. We're suggesting that the flow is very symmetrical, maybe more than you might expect. So I agree. It's a caveat of this model. Let me take my stuff.
Can you get the microphone?
Sure.
Okay, so the next speaker is Nathan Wolf on modeling the
Actually, no, stop.
optical emission from
Maybe I'll take it.
Is this your work? Is this your work?
No. Again, I wasn't. I guess.
So this is the main title. The optical collaboration lines.
Yeah, this is the title. It's meant to match the title of the preprint that we put up last week. But it's we're trying to model both the optical and some other portions of the SED with radiative transfer.
So I guess the idea was that the organizing committee was what would this guy talk about, and this was now the title.
This is what they submitted in the form. This is what they submitted in the form.
Okay, but this just shows us that the field is very dynamic. Working on time scales.
As long as the name of the speaker stays the same.
This is changed. Okay, so 22 minutes and 3 minutes for discussion.
Yeah, just see if this works. Oops. Sure what happened. Okay. So I'm Nathaniel Roth. I go by Nathan. I'm a finishing PhD student at UC Berkeley. My advisor is Dan Kaysen, and I'm talking about work that I've...
Can you put on the
Oh, the microphone. Yes, sorry. Sorry. And so I'm talking about work that I've done with my advisor, Dan Kaysen, and also James Guillachon and Enrico Ramirez Ruiz. And we're all here because SVI and company organized a wonderful conference for us, but the reason they did that is because TDEs are very mysterious. There are a number of puzzles that we're all trying to track down right now, and these are 3 that we've kept in mind throughout the course of our work. The first is what we just heard about, so I won't say much more than that, other than just to reiterate the point that we do see TDEs now over a wide range of wavelengths at optical and X-ray, sometimes simultaneously. And so the big picture that I think we're after here is figuring out, can we predict how often a disruption emits at each of these wavelengths, and then can we use that information to refine our predictions about the rates that we'll see the events at different wavelengths, and then resolve some of the tensions that we currently have between the predicted rates and the observed rates. Something else is the notable lack of color evolution in the optically observed TDEs. So here are just 2 notable examples of that, PS110JH and PS111AF. So as the optical flux dropped, the shape of the optical continuum isn't varying very much. And what this suggests to us is that we have to maybe think beyond simple black body models of the emission, unless for this to happen in a black body sphere, you'd have to have some sort of ubiquitous conspiracy between the luminosity and the radius of the photosphere. And then, of course, there is the question of the optical lines, the great H alpha debate. This is the plot that Yair showed us yesterday with the diversity of spectra, some with broad helium-2 and no signs of hydrogen, all the way down to some that do show both the helium and the hydrogen. And a lot of work to understand this so far has been done with photoionization calculations using tools like Cloudy that are really tailored for situations where the optical depth of the environment is low, but as we'll show later here, a lot of the lines we think are forming in regions that are optically thick to electron scattering, and that will have a profound effect on both the lines and the continuum that you see. So what this suggests to us is that now is a good time for radiative transfer studies to explore some of these questions in detail and, as I said, move beyond simple black body pictures for the flux and understand the emission lines in a more optically thick environment. So to run a radiative transfer calculation, we need to choose some geometry. We have to simplify the problem initially. These are expensive calculations. And so to start, we've taken a spherical geometry. And I want to say a few words now about why that is relevant to the problem, although it doesn't, of course, there's room to improve on our geometry in future investigations. But simulations of disruptions show that in addition to an elliptical accretion disk that forms, you can also have a sheath of material at larger radius that might be intercepting some of the hotter accretion disk light and then re-radiating it at longer wavelengths, UV and optical. And this is reminiscent of a very old idea from Loeb and Ulmer, who predicted before any of the optical TDEs were ever seen that we might see optical emission from TDEs if you have material at large radii. In their case, they were imagining a radiation pressure supported envelope that was more or less static. There are some issues with a picture like this. You need to very finely tune the luminosity to right near the Eddington limit in order to support something like this. Other work has shown that when you exceed the Eddington limit, you might be able to allow the radiation to escape through channels in the polar regions and have something more along the lines of the zebra model that Coughlin and Beagleman have developed. You can also imagine that maybe the radiation does launch an outflow. Linda Struba and Elliot Quadrant did some work on this back in 2009. It's been revisited by Metzger and Stone. And here you do have an outflow, but you also still have this reprocessing idea where hot radiation at the center is intercepted by material farther out. So our current work has been more, it's more directly applicable to the static envelope, although we would like to look at these outflows in future work. And of course, there is now the idea for optical emission coming from circularization at larger radii. And this is also, I think, something we need to follow up with the radiative transfer. There is some connection to this idea and the way we have set up the problem, which I'll explain right now. So we are taking a spherical domain. We have an inner boundary and an outer boundary that we can adjust. We use a density power law that we chose to be r to the minus 2, although that could also be adjusted in future work. And we put in some thermal spectrum at the inner boundary, which is usually peaking in the X-ray or the extreme UV. And we choose the temperature of that inner emission to correspond to what you would find from the radiative diffusion equation. So for the optical depth of the envelope and for whatever luminosity is coming out at the center, you can find the energy density at the inner edge of the envelope, and you can translate that to a temperature. And then by adjusting the position of this inner radius, for example, by moving it out to several times the tidal radius, you can crudely incorporate the idea that you're getting dissipation not all from very close into the black hole, but also farther out. So the radiative transfer that we're doing is with Monte Carlo, and we alternate between solving the transfer equation and then solving the non-LTE rate equations, which give us ionization states and atomic level populations. And we track all of the bound-bound, bound-free, and free-free transitions. Well, I should say we track about 1,000 of the bound-bound transitions and a few hundred levels for the bound-free. We also have free-free processes, some collisional processes, although they tend to be subdominant to the radiative processes for controlling the ionization states of the material. Some simplifications to keep in mind. The composition of the envelope that we're looking at initially is hydrogen, helium, and oxygen, not other metals so far, just because it takes additional work to do the atomic modeling to include the other metals. Not that we don't think that they won't be, they could be important for some of the details of the lines that we see, but I think a lot of the general results still hold even with just the limited composition that we're looking at. We are using solar composition, so the hydrogen in all of the calculations I'm going to show you is about 10 times as numerous compared to the helium by number density. I already explained the power law gas density, the inner boundary. Okay, a big simplification to keep in mind is the way we've treated the line widths so far. So we've just, for the absorption and emission everywhere in our envelope, we're using a Gaussian line profile with a width of 10,000 kilometers per second, which was inspired by observations like PS110JH. And that is something that we also plan to explore in more detail in future work. I'll skip over the details about the way we're doing the non-LTE physics. Aficionados can ask me about this later, but I'll just jump now to the results. So here are some spectral energy distributions that we get coming out of our calculations. So on the horizontal axis is wavelength, covering all the way from 10 angstroms to 10 to the 4 angstroms. Lambda L lambda in ergs per second is on the vertical axis. And the two dashed curves that I've shown here are two different inner X-ray spectra that we put in that correspond to different locations of that inner radius. The colored curves are the reprocessed light that comes out. So you deplete some of the soft X-rays, and you get a fraction of them coming out at longer wavelengths like the UV and the optical. And if you integrate the optical luminosity here, you get a few times 10 to the 43 ergs per second, which is about what many of the optical observations show us. In these particular cases that I've showed you, you also get a lot of the X-ray coming out. And the reason that's happening is because even though the electron scattering depth is very high, the absorption optical depth is not necessarily very high at all wavelengths. Some of the ionizing photons can just scatter all the way out without ever being absorbed because the material is so highly ionized. Now, this doesn't always need to happen that you get all the X-rays out like this. We've experimented with dropping the luminosity, and here I should mention that this is dropping the luminosity, keeping everything else fixed. So this is not necessarily meant to show you a time series for a given event. This is just trying to build intuition for what happens when you change just the luminosity. Yes?
A quick question. What is the outer and inner radius in terms of propagation of the net for the black hole mass?
So the mass of the black hole does not enter directly into this calculation. We just chose a luminosity here of 10 to the 45 ergs per second. So you could, if you want to say a 10 to the 7 solar mass black hole will have, this will be the inner radius is for us tends to, in some cases, up to 100 times the gravitational radius.
Can you say again what is the calculation you're doing exactly? You have a mixture of 3 elements you mentioned. You assume it's a spherical situation and you release that luminosity in the center of it?
That's right. And so we're looking at a steady state solution. So we're not following the time evolution. We can just vary the parameters and then see what the final converged solution looks like as it changes. The diffusion time for us is about a week or two. So we're sort of imagining near peak and not following it for a time much longer than a few times 10 to the 6 seconds. What does the radiation that you emit at the inner boundary, what does it look like when it escapes? And that's...
So it's a steady state calculation with a given luminosity spherical.
That's right.
And you deposit the energy at about 10 to 13 centimeters?
Um,
Is it relative to the...
Yeah, the blue curve is 5 times 10 to the 13. We tried even smaller also, and it looks similar. You just shift you just imagine shifting the peak of the soft X-ray to smaller wavelengths, and it doesn't have a big effect on what comes out in the optical. Let's see. So that is, yes, I think that is helium, oh, okay, 1800. Okay, 1800, sorry.
No, I'm just guessing the V on the scale.
So there's something going on at like the Lyman at 1200.
There's a chart, you know, that looks sort of, it's a little hard to gauge because it's a log scale.
Yeah.
But I don't know, if you information carbon 4 or...
Well, so again, we don't have carbon, so that might be an oxygen line. I should go in and identify which line that is.
It looks like a big feature, and I was wondering if that is robust against other parameter changes.
So I've been focusing mainly on the lines that we see in the optical, but I think we definitely want to do more predictions for the UV. Yeah. So I haven't had a chance to really compare in detail to the UV observations just yet.
And the dominant cross-section in this situation is scattering or line or...
So scattering is the dominant opacity throughout, and then what's absorbed? Electron scattering. Yeah, and so the primary process that is absorbing the soft X-rays is photoionization of helium-2. And in the optical, the primary absorption processes are either hydrogen photoionization or free at wavelengths greater than the Balmer break, so at 3,500 angstroms and longer. Here's what happens when we adjust the mass of the envelope, keeping the luminosity fixed, and the optical flux moves down while the shape of the continuum remains relatively constant, which is reminiscent of some of the data that I showed you earlier for events like 10JH. There are many steps to go before we say, well, this is exactly what is describing the evolution of the light curve. This is, again, just varying the mass, keeping everything else fixed. The point, though, is that this is just another aspect of the problem to keep in mind about how optical flux relates to parameters of the problem and how you can adjust the flux without adjusting the shape of the continuum. So how much time do I have left? Okay. Okay. So let's take some time now to look at the spectra. So here are 3 spectra for envelopes where the parameter we varied was the outer radius of the envelope. And we've rescaled the units here so that all of their continua overlap right at 6,000 angstroms. And that was done simply to make the trend in the H alpha equivalent width more apparent. But what you can see is there is a transition where the H alpha sticks up noticeably above the continuum and then moves down and blends into the continuum. In fact, it moves into a slight absorption feature. And that's what we showed here when we subtracted off the lines and a power law continuum, which is the fit to what we have at these wavelengths. And what we see is a range of line ratios. So for the blue, it's about 2 to 1 helium to hydrogen. For the green, we have 5 to 1, which is that constraint that it's right where PS110JH is constrained to be. And then for the red, when you look at the actual spectrum, it moves into a shallow absorption feature here. But if you look back at the actual spectrum, especially with there's noise around the data at long wavelengths, it would be hard to distinguish from just pure continuum. So to understand how this is happening, we need to think a bit about effective optical depths in a scattering-dominated atmosphere. So for a given process, if you want to know how deep into the atmosphere you're seeing the emission from that process, you need to consider something called the thermalization depth, which is approximately 1 over the square root of something called epsilon, where epsilon is a ratio of whatever is the absorption opacity to the total opacity. And you can derive this effective optical depth from a random walk argument. It's an old result that goes back many years and underlies a lot of work on stellar atmospheres. And then to predict the flux that comes out at a given wavelength, you need to consider the thermalization depth at that wavelength and then integrate the emissivity in the volume extending from around the thermalization depth to the outer edge of the system. And so this is a plot where we try to show how this works at a glance. I've been thinking about ways to make this more clear, but I'll try to walk you through it here. So the y-axis is integrated emissivity. So we take J lambda ergs per second per angstrom per solid angle, multiply it by 4 pi. That's the that gets rid of the solid angle, and then integrate 4 pi J lambda times 4 pi r squared dr. So you're integrating that emissivity over a volume up to the indicated electron scattering optical depth on the horizontal axis. And then you stop at a given wavelength, the flux that comes out, you stop at around that thermalization depth for that wavelength. And so if we look at the red and the orange first, so orange is a continuum near H alpha, 6,000 angstroms. And the thermalization depth there is relatively far in, close to 30 electron scattering optical depths. And we want to compare that to what's coming out for the line plus continuum at the H alpha wavelength. So then for that case, you would add the contribution of the red and the orange curve together at the marked thermalization depth with the red dot. So you add those two together and you get something pretty comparable. So the H alpha is not going to stick up far above the nearby continuum. If you do the same exercise for the helium, the continuum for the helium is coming also from around 30 electron scattering optical depths. The helium line is less opaque to itself, so its thermalization depth is deeper into the envelope compared to what was happening for the hydrogen. And so when you add together the continuum and the helium at the 4,700 angstrom line wavelength, you get something that will stick up notably above the continuum. So I'll put up my conclusions here. I think the main takeaways are that this is a good time for more radiative transfer studies to connect all of the detailed hydrodynamic work that's being done to the observations. For the optical observations, we've shown that there's likely to be a lot of emission that's coming out at UV wavelengths and soft X-ray wavelengths that you might not be accounting for if you try to estimate the bolometric luminosity from fitting a single black body to the optical observations. And TDEs with simultaneous optical and X-ray coming out might be arising from these situations where you have partial absorption of the X-rays. And the line transfer is highly sensitive to optically thick effects. There's lots of room for improvement. I've mentioned a lot of those along the way, but I'm happy to now to hear your suggestions about future work. Thank you.
Thank you.
So you mentioned the metals.
Yes.
Do you have a sense of how far into the optical and how much of the spectrum?
It's a little hard to estimate. I will say that when we started with just hydrogen and helium and no oxygen, and then later we added in the oxygen. And by adding in the oxygen, we saw a lot of new line features, especially near the 100 especially near 100 angstroms that weren't there initially. But the optical continuum and its behavior didn't change very much. The H alpha and helium line ratios didn't change very much. So my guess is that for comparisons to UV spectra, like the assassin event that we've been talking about, and for future observations, we'll need to include all those extra metals. But for some of these early questions that I tried to motivate at the beginning of the talk, I don't think it's super sensitive to that. Our experience so far is that I don't think so. I mean, maybe at small quantitative levels, but the qualitative trend I don't think will change. Yes?
In an earlier slide, you showed H alpha coming in and out of existence as a function of our outer.
Yes.
And do you have a physical explanation of what's going on, why that's existing?
I've been thinking very hard about that. I haven't really arrived at a good intuition for that yet. It's a little complicated because what's setting both the emissivity and the thermalization depth are the exact level population distributions, which are given by this non-LTE rate equation matrix. And then we also need to be tracking that as a function of radius. And when we change the outer radius of the envelope, we're changing the densities in both the regions where the opticals, where the continuum's coming from and where the lines are coming from. And so I haven't really found a clear intuition for how all of that, at the end of the day, gives you that nice systematic trend without a radius. But it's something I want to keep thinking about. Yeah, well here, you can even see it here. There's something that's happening with the H alpha line as you vary the mass. So if you look at the purple curve, there's two spikes happening in the optical down there. That's the helium and the H alpha. And the H alpha is not really being seen for the higher mass cases. So this is another parameter where the H alpha comes in and out.
It might be fun to see how you think you can go away and sometimes does.
Yeah, definitely. The strength of the helium line is changing as well. We focused on the ratio to the hydrogen, but its equivalent width is changing as well. And it would be great if we could get a featureless continuum. We haven't gotten that yet, but that would be interesting to find.
I guess I guess the question for the observer. So your spectrum is much flatter than a black body. Does that actually get you to the black body slopes that are usually probably genes that you're more like lambda 1 or something?
I showed yesterday in the discussion actually these moments of split data, and I think our observations still can distinguish exactly what I think.
Yeah, I've been thinking about that too. So 10JH is a case where it really seems like you're seeing the Rayleigh gene's tail. There are other observations where people have been saying, well, maybe you're getting close to the turnover off the Rayleigh gene's tail, and you can fit a black body there. But you could also fit a power law there with a slightly shallower slope than Rayleigh gene's. But I agree that I think this is a lingering question for us. Is there a way that we can get the optical continuum slope to be steeper? So far, we've had trouble doing that. Maybe if we consider more of a shell geometry rather than having the emission extending over such a wide range of temperatures, that might be one way to do it. Yeah.
Yes, I think if you measure alpha, so the spectral index slope instead of the black body, you get around 1 sometimes. So I don't think you should change your model to get on the Rayleigh gene scale. But my question was, so you have a steady state model, but based on the sources of opacity that you identified that are dominant, can you say something about the diffusion time scale for converting X-rays to, say, optical?
Yeah. So the dominant the dominant opacity for setting a diffusion time is the electron scattering opacity. and we can do estimates of that, what the diffusion time should be, and we can compare it to our numerical results. And most of the optical depth is at smaller radii. Because we have this power law, most of the scattering is happening at smaller radii. So you don't have to, the fusion time is optical depth times radius over the speed of light. The question is, what radius might you need to use there? And it's actually, we see it's more appropriate to be using the inner radius for the density configurations that we saw. And so you get, both from that estimate and from the Monte Carlo, a diffusion time of about 10 to the 6 seconds for, say, this red curve here. So that's a week, something like that.
What is your signal density, fallible density?
Yes, we are taking r to the minus 2 is what we settled on. So that is the same density profile that you would get for a steady state outflow. There are ways that you could get a power law like that for a more static envelope. So these zebra models, for example, have density power laws that range from r to the minus 1.5 to r to the minus 3. We have tried exploring steeper power laws. The calculation does become more expensive the steeper the power law, because then the density at the inside gets higher, and we have to spend more time watching the photons diffuse in the inner region then. But this is the flattest that we've tried so far, but yeah, we should explore that parameter too. Brad's been waiting in the back.
No, sure. I mean, I want to understand what you said with your steady state calculation. Even if you haven't said yet, you were to evolve time,
what we're imagining right now is sort of a sequence of things like this. So at any given moment, one of our calculations can tell you what the, sorry. Go. So at any given moment on the light curve, you can take parameters from our calculation and try to match that to what's seen. And the time scale for the SED we're generating to adjust is short-ish compared to the time that the total light curve is evolving. So we're hoping that these snapshots can tell us about what's happening at moments in time. But the real way to do it would be a time-dependent calculation, where not only are the properties of the envelope changing in time, but you're also needing to involve that with the diffusion time of the envelope, and that might have something like that.
Okay, thank you very much. The last speaker in this part of the session is CA. The title is Soft X-ray Temperature TDEs from Stars Disrupted and Heat Plunging Orbit.
Hi. So I'm Li Xin, and I'm happy to talk about soft X-rays TDEs today. Is it coming back?
If you go the connection, it's
Maybe
changed.
the connection. Okay, that's it. Just don't move.
Okay. Okay. And the main model is from stars disrupted on deep plunging orbits. And for the work I'm going to present today, most of the results is done with my collaborators, John McKinney and Cole Miller. Thanks. And the result was just published in actually later last month. I'm supposed to be flipping. It's not working. And it's not working here either.
So now it's stuck.
Okay.
Can you try just using
Yeah,
the
I'll just use the laser
Yes,
pointer.
okay.
Thanks. Yeah. So far, observationally, we have observed about 30 TD candidates. I think I don't need to go through them with you again. In the later session today, you're going to hear about soft X-ray TDEs. These are the earliest detected TD candidates. There's interesting UV optical TDEs and their lamp profiles. We have observed TDEs in hard X-ray gamma ray from the jetted events, and also radio signals have been detected with both the jetted and non-jetted events. And also ongoing and upcoming emissions are going to boost the sample size up to by a factor of 100. So with a lot of upcoming spectral emission profiles, the key question is, in my mind is, are we seeing the same type of beasts? Are they different beasts, or are we seeing the same elephant, but we are blind people touching different parts of it and we think they're different beasts? So in my talk today, I'm going to focus on the soft X-ray TDEs because I'm a theorist and I like cleaner things. And I think soft X-ray TDEs are cleaner. They must be from the accretion disk. Well, for the optical UV TDEs, they could be from the disk or the reprocessing of the photosphere. They could be from the circularization energy. It's less clear to me what is going on with them. So before I start my theoretical talk, I would like to show you a very nice figure plotted by Stone and Metzger. And here is some distribution of a bunch of TDE samples. And it seems to me the UV optical, I'm sure he's going to talk about this more tomorrow on Thursday. It seems the UV optical TDEs are more concentrated around black holes of mass a bit less than 10 to the 7 solar masses. And the X-ray gamma ray TDEs seem to have a flatter distribution with a little bump around 10 to the 6 solar mass black holes and another little bump around the very massive black holes. So for the soft X-ray TDEs, these are, I'm going to talk about, these are not the jetted ones. And the black body temperature, as listed here, is mostly between 10 to the 5th to 10 to the 6th kelvins. So why X-ray temperature for these disks? So if you like people, ask people like Martin Rees 20 years ago, and he will tell you, oh, all the TDE should be in soft X-ray temperature. And as you have heard many times in the previous talks, the reason is very, very simple. In these old pictures, the circularization is thought to be magically happening around the pericenter, and you form a very small disk. So for this very small disk, it is not just the inflow time scale is very short. So the accretion rate and the light curve would trace the fallback rate. But also, because the fallback rate for most of the systems are super Eddington, if the black hole mass is not bigger than roughly 50 million solar masses, then the accretion rate is also super Eddington. And if you distribute Eddington power across this small photosphere or across this small disk, you get a black body temperature which is peaked in the X-ray. And of course, as you have heard in the wonderful talks yesterday and this morning, the circularization turns out to be rather inefficient, either through the nodal shock of the pericenter passages of the stream or through stream-stream collision and caused by the apsidal GR precession and the energy loss through that. So what does that mean? That means the disk will take some time to form. The simulation of parabolic TDE suggests the disk could be rather extended and the accretion rate could be 10 times or even less than the peak of the fallback rate. So if that's the case, it seems rather hard to produce a very luminous X-ray flare as we have observed in some of the TDEs. So I was thinking about this problem. I was playing with the parameters to see if there's a way of recover the classical picture. And I found the key thing to recover this classical picture is to have a high accretion rate and a small photosphere. And the magic I found is to have deep plunging stellar orbits or high beta stellar orbits. And what is a high beta orbit? So let me remind you again, what is beta? Beta is the penetration parameter. It is defined by the tidal radius divided by the pericenter distance. So for fixed star black hole disruption, RT is fixed, but you can always vary RP so the star can penetrate through deeper and deeper into the potential well of the black hole. And when beta is bigger, that means the orbit is closer to the black hole and the stream is affected more by the gravitational effects, affected more by the GR effects. So what's the difference between a low beta and a high beta encounter? They would matter for, as I'm going to show you in the talk, they will matter how fast circularization happens, where the circularization happens, and also what is the eventual size of the accretion disk and temperature. So here is some simple illustration of a fiducial setup of a tidal disruption event using a solar type star disrupted by a 1 million solar mass black hole. on a beta equals 1 orbit. The star comes in a parabolic orbit, is disrupted here. A while after disruption, the tidal stream is rather elongated. So most of the earlier tidal falling back materials is going to be along this most bound orbit. And from the parameters of the mass ratios and stellar orbit, we know the size and eccentricity of this orbit. After the head of the tidal stream falls back and passes very close by the black hole, it gets some GR absolute precession and is deflected on the way out and is going to collide with the trailing part of the tidal stream. And that is why you see the collisions in all these wonderful GR simulations, as people have shown yesterday. And you know what is the precession angle over one orbit from GR, which depends on the size and eccentricity of this ellipse. And for this setup, you would see actually the tidal radius is at roughly 50 Rg, so the absolute precession is weak, and the intersection happens rather far away, close to the epicenter of this most bound orbit. So keeping the outer parameters the same, but if we just increase the beta parameter to be a larger value, and you will find the absolute precession angle is bigger, and the tidal streams intersect much closer to the black hole. And here I'm just showing this plot. This is the same setup as in Shirokava's simulation, the disruption of a white dwarf by an intermediate mass black hole. To show you, in this situation, in this simulation, the absolute precession is also rather weak. So this is closer to this simulation, to this situation, rather than this situation. And also, we can find what is the interception radius and the collision angle when the two streams collide. And they turn out to be rather simple equations of like the eccentricity and other quantities, which are basically, eventually they're just functions of the mass ratio of the star and the black hole, and also the beta parameter of the stellar orbit. And here I'm plotting the interception radius in gravitational units, and the x-axis is the mass of the supermassive black hole. And the black curve is for the beta equals 1 encounters. And this is for higher and higher beta encounters. And as you can see, and it's the same with your intuition, if the beta keep the same mass but increase the beta, then you would find the intersection collision angle. Why do we need to know this? Because the energy loss when the two streams collide and how fast the circularization happens would depend on these two quantities. So what is the energy loss at the tidal stream intersection? So we assumed a very simple assumptions without doing any hydro simulations. We assume that outgoing stream and the incoming stream have similar momentum, and also the collision is totally inelastic. And of course, this is the upper limit of the estimate of the energy loss. So this is saying after collision, the two streams merge and they move at the same speed. And as you can have seen from the simulations, or in actually the reality, like there will be lots of more complicated things going on. There will be mixing of materials, deflection of the tidal stream, shocks generated, and redistribution of angular momentum, lots of things going on there. And also for these high beta encounters, as for example, you have seen in Clement simulations, you see the tidal stream could go through each other for several times until they finally settle onto like one stream. So my interpretation of this energy loss is, so the energy loss must be a function of the collision speed, and the higher the collision speed is, the more energy loss there will be. And it should also be a function of the collision angle, and the bigger the collision angle, the more the energy loss is in the stream-stream collisions. So you should take this as an order of magnitude estimate of how much energy is lost. And it is not necessarily the energy loss in the first intersection. It's more or less like after several intersections, when things relatively settle into one stream, this is the total energy loss. And also we can estimate we can calculate what is the stream with the collision speed of the tidal streams from where the intersection radius is. And for hybrid encounters, they intersect much closer, so the speed here is higher. That's why the energy loss here is much bigger than here. So from the energy loss in the tidal stream, we can estimate the size of this elliptical accretion disk formed after collisions, which is the initial phase of the disk. And for hybrid encounters, the size of the disk has a very simple relationship with the intersection radius and also the collision angle. Okay, so plotting the size of this elliptical disk, y-axis is the size in gravitational unit, x-axis is the mass of the black hole, and similarly for different beta encounters. And actually, the size of the disk behaves rather similarly to the interception radius. So the bigger beta is for the same black hole mass, the smaller elliptical disk it forms. And here I also plotted in dashed line the classical circularization radius, which is 2rp, which is assuming the angular momentum is conserved in the circularization radius, circularization process. And you can see actually for high beta encounters, or like high, very big mass black holes, the elliptical disk size is not that big compared with the classical radius, the classical circularization radius. This means they are more or less circularized, or they can circularize very fast. And for these low beta encounters, especially here, it seems the disk is still extremely elliptical. So I'm not certain what is going to happen here. Perhaps this is going to be Jerusalem bagel model, or perhaps there is some circularization is needed before the thing, most of the thing accrete onto the black hole. It is possible that this can retain some elliptical configuration while accrete onto the black hole, or full circularization may never happen. So we are still waiting to see a hydrodynamical simulation on this to confirm. Okay, and if we plot the number of collisions needed, basically, not just by naively taking the total energy the stream needs to allow us to go into full circularization divided by the energy loss in the collisions each time, this is roughly the number of collisions it takes. And again, this is only an order of magnitude estimate. What I will take from this figure is it's telling us like in which regime what physics is going on. So I would say within, like below the blue line, the circularization is going to happen very fast, and above that is going to be slow, unless some magic things can happen. And also to the left of this purple reddish line is going to be in the super-Eddington regime, and to the right of it is in the sub-Eddington regime. So for example, for 10 to the 5th solar mass black holes, no matter how slow the circularization is, the accretion is going to be in the super-Eddington regime. For things like a few times 10 to the 6 to 10 to the 7, it depends on the beta parameter. And for very massive black holes beyond 10 to the 7 solar masses, everything is sub-Eddington, even if the circularization happens very, very fast. Okay, so the X-ray TDE's model I'm going to talk about is mainly in this regime for the high beta encounters, and they're super-Eddington TDE accretion systems. So how much do we know about super-Eddington accretion flow? Not until very recently people have started to do simulations to understand them better. So for example, one of the experts on this is Oleg Sadowski. In their simulation done this year, they have found in the super-Eddington accretion disk, and these are very large extended disks, not necessarily TDE disks. The disk is very thick, extremely thick, both geometrically and optically. And also a lot of outflow is generated on the surface of the disk. And these outflows are completely optical thick, and they are very extended in opening angle. So this means the inner part of the disk is going to be obscured. You're not seeing through something here, but only the outer part of the disk, or the photosphere, or the outflow. And also in another super-Eddington simulation done by our group, GRMSD simulation with a jet triggered, we find similar results, but also the photosphere would have a viewing angle dependence because the jet would change the configuration of the photosphere. And what is the luminosity in these super-Eddington systems? as Roseanne talked about yesterday, there is still a debate by various groups, but it seems that the luminosity is thought to be either around Eddington or slightly above Eddington, if there's no jet. Okay, so if we adopt the results from those super Eddington simulations and apply them onto TDE accretion disks, what do we think we know about these disks? So the disk is very small compared with the AGN disk. It is going to be optically thick and geometrically thick. I did a calculation with the outflow, and I found it to be optically thick close by, and the optical depth is going to be less than 1 beyond the size of the disk if it has a very extended opening angle. So that means the photosphere of this system is going to be roughly the size of the small disk. And inside the photosphere, we are probably not seeing through the most inner region of the disk. So that is why the temperature we see is going to be the surface temperature of this photosphere. And we can calculate this temperature by setting the luminosity of the system to be kept by the Eddington luminosity if the accretion rate goes beyond the Eddington accretion rate. And we can plot the effective temperature using this relationship. But before that, I want to point out for these high beta super Eddington accretion systems, everything is going to be obscured by this photosphere with Eddington luminosity. So either the accretion power or the circularization power is beyond the Eddington luminosity. So, but then if everything is obscured, there's no way of telling where the power is coming from. Okay, so showing a bigger figure of the temperature of these events. The y-axis is the temperature and the x-axis is the black hole mass. The color scheme is the same. So for example, for the beta equals 1 encounter, we find the temperature increases first with the black hole mass and then eventually decreases when it goes to very high. And also for the same black hole mass, of course, if we increase the beta, then the photosphere size is smaller, then temperature of that photosphere is higher. If we draw some division between X-ray events and UV optical events to be here, then we will find the X-ray events favor high beta cases, beta roughly bigger than 3, and also black hole mass on the small side, less than 5 million solar masses. Okay, so we think that could be responsible for the bump here. But as you see from this figure, there is also a bump on the very massive side. What are those X-ray DDEs? So it turns out these ones are even easier to explain. So in the 10 to the 8, for 10 to the 8 black hole masses, the fallback rate here is sub-Eddington. So the accretion rate must also be sub-Eddington. So that means the accretion disk is no longer super Eddington thick disk. It goes back to the standard Sakura's NEF thin accretion disk. And there is some wiggling room of the mass estimate here. But for very massive black holes, they would favor a spinning black hole case actually for stars to be disrupted outside the event horizon before plunging into it. And also, these events must happen very close to the black hole, so GR is dominating the dynamics there, because the tidal disruption radius divided by the gravitational radii is actually a negative polar law function of the black hole mass. So for 10 to the 8 solar mass black holes, everything happens within the tidal disruption happens within 10 gravitational radii. And that's why the GR absolute precision must be very strong even for low beta encounters here. And the tidal stream intersection is also happening very close to here, to the event horizon. So circularization must be really fast. And also for this Sakura's NEF thin disk, there is actually not much room for it to grow beyond. So the intersection radius is within 10 gravitational radii, and also the ISCO is varying between like 1 and 9 gravitational radii depending on the spin. So this disk is really, really very, very small, and therefore the temperature of this thin disk is basically the same as the ISCO temperature. And if you remember, the ISCO temperature for 10 to the 8 solar mass black hole is actually in soft X-ray. Okay, so that's the main message of my talk. The circularization speed, where the intersection depending on where the intersection happens, and this depends on the beta and the mass of the black hole. The mass accretion rate is more sensitive to when you vary the beta parameter than the mass of the black hole. And there seems to be two ways of producing soft X-ray temperature TDEs. One is for TDEs happening on the smaller side of the mass spectrum. These are super Eddington high beta encounter events. And on the very massive side, these are just very small thin disks with the ISCO temperature in soft X-ray. So that's my talk. Thanks. This is not actually, this is interesting. That's a good question. Yeah, I can repeat the, yes. So he is asking about this turning point. So, I mean, so first here, like, here we are assuming, we're just taking the black holes to be non-spinning. If you have a spin, like, of course, this would not be that accurate, but this is actually because of the collision angle. Yeah. I think even if you're right, yeah, the energy loss could, yeah, but I mean, you shouldn't trust things too much here, basically. Yeah.
Can you comment about the debate, specifically, so at the low mass you require beta to reach the soft X-ray?
Yeah, that's a very good question. What is the rate of these high beta encounters? They are going to be low compared with like low beta events or partial disruption events for sure. I mean, it depends on the full loss cone or empty loss cone scenario. In one case, the probability of having like less than beta, bigger than beta encounter goes as 1 over beta, and the other one goes as 1 over beta square. I forgot which one is which. But so the high beta ones are going to be small, but the sample of X-ray TDEs we have is also small compared with the optical TDEs.
In regard to the high mass cases, where there's sub-Eddington by a little, why wouldn't the continuum spectrum look basically like a quasar, except that it's cut off at long wavelengths because the disk doesn't extend out very far? And quasars don't peak in the soft X-ray.
Do we know where the X-rays in quasars come from? I mean, maybe they're from corona.
Well, the typical story in quasars is indeed people attribute, and I think that's a pretty good reason, attribute the hard X-rays to a corona. But that's not the majority of the light. In nu L nu terms, they pretty generically peak in the ultraviolet.
It's a reflection.
No one knows why, but empirically we see it.
Nothing when there is like spinning it from its maximum speed, then you can get it a little bit closer to the temperature.
Not going to gain you much.
There's reflection reprocessing that flares up a little bit and it intercepts some of the light from the inside. That's been the explanation. There's a debate whether it's actually reprocessing of the light or if it's just solely.
That's forgetting the tail. That doesn't change the peak.
Yeah,
you're looking at it.
Right.
They get the big blue blob.
Yeah, but it doesn't change the peak of the emission.
Well, I mean, there's two peaks. There's the big blue blob, and then there's the soft X-ray peak. And the big blue blob is fire.
James, there's no empirical evidence for soft X-ray. And the usual reprocessing story has to do with coordinating fluctuations along the wavelength. But those are still a minority of the light.
Yeah, I'd just like to add a quick caveat and comment to the figure from my paper about the distribution of black hole masses and TDEs.
Sure.
So I think to some extent take this with a grain of salt. All of these masses were taken from galaxy scale relations, which have so much rate scatter in them. That's why this curve has widths rather than it's continuous rather than pure because there are different errors with each black hole mass movement. But to put this in the context of circularization, take the typical mass of a star drum behind that gets disrupted, which is 0.3 solar masses, that peak at 10 to the 6.8 solar masses corresponds to a pericenter of 8 RG, and a beta equals 1 event has a pericenter of 8 RG, and that same beta equals 1 event has a self-intersection radius of 80 to 90 RG.
Mm-hmm.
So those are self-intersections that are quite close.
So you mean this peak?
Yes.
Okay.
If you're looking at a typical low mass star getting disrupted, so I think that does correspond to self-intersections that are happening during the black hole.
Sure. I mean, it is possible, like there's some reprocessing going on, and that's changing some of the X-ray into optical. I mean, that's definitely not accounted for in my model. Like I just have this X-ray emission black body surface, but it could be a viewing angle dependent thing. It could also be reprocessing. So we can talk about that later.
Okay, I think we should stop here. I think we should appreciate my success as a chairman. All the speakers spoke at least 1 minute less than the time that they allocated to them. Still, the session is 15 minutes late. My achievement. And because of that, we will resume 15 minutes late with we'll begin at 11:20. Unfortunately, we reached the lunch break, but we're not that hungry. So we resume at 11:20 for the next part of this morning.